So please tell me, can you see this? Can you see this? Please tell me. Am I audible? Sorry. And now, am I audible now? Please tell me, am I audible? Are you see the blackboard clearly? If not, please tell me. I'm waiting. Yes, okay, thank you. So, V is a vector space S and T both are subspaces of V. I have already defined in my previous class, that is S plus T, that is the direction, which is a vector space. It is a collection of vectors V curl such that V curl equal to X curl plus Y curl, where X curl belonging to S, Y curl belonging to T. And this decomposition should be unique. This is the definition of direction which I already defined. So this X curl is called projection of V curl, into S along T. And Y curl is a projection of V curl into T along S. Then S is called complementary space of T, and T is called complementary space So for explaining this, I have considered in my previous class, that is R cube, R square. So this R square is our V. I have considered S as a collection of vector where X belonging to R and T is another subspaces x x which is belonging to where x belonging to R. So if you draw this, then you see that then you see that this entire space is our R square, and any point lies on this line is your S, and any point lies on this line is your T. Suppose you take any point in R square, say 1 comma 2. Then 1 comma 2 is your, if you divide this as, then 1 comma 2 is here. This is your 1 comma 2. Now this 1 comma 2 is nothing but this, but this vector is your x curve which belonging to S, and this is your v curve, y curve is belonging to T, and this is your v curve. So x curve lies on here. This is -1 0, which is equivalent to -1 comma 0. So this is a -1 0 is the projection of what? This vector 1 comma 2, where it is into S, and this is parallel to or along or parallel to T. Similarly, this 2 2 lies in here. This is 2 2. So 2 2 is a projection of one 2 into S along or parallel to projection of into where it is T, into T parallel to S. Yeah. So this S and T, you also check that this give direct sum which is contain only one element, that is origin. So S and T are disjoint, and S plus T is direct sum gives R square. And this S is called or com complementary space of T, and T is called complementary space of S. So you can take another T. Suppose if your T is, say, zero y, where y belonging to R, then then your then this is the entire space is your R square, and this is your S. Any points lies on this line. This line is your S, and any points lies on this line. This is your T. So if you take any vector that is 1, 2, so it is here, and you see that this is 1, 0 plus 0, 2. So 1, 0, this is your 1, 0. Now you see that 1, 0 is a projection. 1, 0 is a projection of 1, 2 into S along T. And again 0, 2 is a projection of 1, 2 into S along T. So you see that if you take different S and T, your projections also change. So these are the examples. I think I think the order of, I want to, okay. If you take another example, say RQ. RQ, if S is equal to collection of X, Y, Z, where X is equal to 1. So this space is a subspace of RQ, and here we see that these are the, this form the basis of S basis of S. So the canonical basis of RQ, we know these are canonical basis. So now is it okay or anything problem? Oh, hazy. Okay. Now it's fine. It's fine. Please tell me. Now fine. Okay. Thank you. So these are the basis of S, and this is the canonical basis. Or you just write, don't just erase the prime, just write 110 or 001. So these are the basis. This form a basis of S, and this is the another basis. This is a basis of R cube. So basis of R cube. Okay. So now we take another subspace T whose basis. So if your P is a complementary space of S, then you see that this vector already is here, and see that 100 or 010, if you take any one of them, either if you take 100, then you see that this is a independent vector. This is an independent vector because you cannot write this as a linear combination of this. Why? Just check it. Canonical basis is a simple standard basis. Canonical basis is a standard basis. So for Rn, it should be if you take Rn, actually these are the axial points. For example, if you take R square, axial points are 1001. So this is the canonical basis for R square. For R cube, so this is for canonical basis for R cube, and Rn. We generally write it as E1 curl, E2 curl, E1 curl, E2 curl, E3 curl. Similarly for Rn, this should be E1, E2, En, where Ei curl is a vector whose ith element 1 and other elements are 0. Clear, Ankon? Tell me, this type, this basis called canonical basis or standard basis? Ankon? Ankon, clear? Okay. So 100, you cannot write 100 as a linear combination of these two vectors. See that C1110 plus C2001. This gives you C1, C2, C3, C1, C1. Sorry, C1, C1, C3. So if you choose C1, 1, so you see that you have there is this is not equal to 100 because you see that if your C1 is non-zero, you cannot get this value 100, even if your C3 is non-zero. In that case, you cannot get 100. So 100 cannot be written as a linear combination of these two vectors. Hence, 100 is a independent vector, or you write this set 100 110 001 is a set of independent vector. So instead of this basis of RQ, we consider this is another basis of RQ. This is another basis of RQ. So you see that these two bases forms these two vectors generates S, and if you consider these vectors and using this vector, if you generate T, that is linear combination of C3. Oh, okay. C3 is C. My claim is wait. I am answering your question. Okay. So claim is this is a independent vector. The set of linearly independent vectors. Okay. So these are it. C1, C2, C2 and C3 are both are scalar. Whatever in C2 or C3 doesn't matter. Okay. So I assume that these are the dummy variable. Okay. So does it make sense? Okay. You can take C2 or C3. These are same things. So the claim is this set is a independent set of independent vectors. So first assume that this is not independent vectors. Then you should write. Then it is possible to write any vector can be written as a linear combination of remaining two vectors. So already we know that these two are independent because this construct the basis of S. So if this set is a set of linear dependent vectors, then this should be written as a linear combination of these two vectors. Okay. So this is assumptions. So this should be write as a linear combination of C1, 1, 1, 0, C2 or C3 doesn't make sense. If you want C2, fine. So C1, 0, 0, 0, C2. So C1, C2. Therefore, C1 equal to 1, C1 equal to 0, which is a contradiction. Hence, the claim is true. This is a set of independent vector. Clear, Swarnabu? So, Swarnabu, again, C3 and C2 are same thing. Okay. C1, Swarnabu, clear or not? Tell me. So, can I write this thing? This is a set of independent vector. Okay. Thank you. So now you see that since this is a set of independent vector and the number of vectors in R, dimension of R3 is 3, so this again a basis of RQ. Clear? Now you see that these two vectors gives the basis of S. So T, which is your complementary space of S, so this is just a linear combination of the vector 1, 0, 0, where lambda belonging to R. So this okay. So if you so now S is your and T is your and take any vector and you see that RQ can be written as a direct sum of S plus T, and any vector in RQ, say 1, 1, 2. This is written as a linear combination of the basis of R cube here. C1, if you compare both sides, then 1 equal to C1, 1 equal to C1, and 2 equal to C2 plus C3. So if you take C2 equal to 1, C3 equal to 1, sorry, C1, write this thing first, C1, sorry, I write the same vector thing. This should be 1, 0, 0. 1, 0, 0. C3 equal to 1, 0, 0 because these are the base. This is the basis of R cube, and this vector can be written as a linear combination of these three vectors. Then you see that 1 equal to C1 plus C3 and one equal to C1, 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 0, that is C1, 0 plus C3, then C1, C2. So C1 equal to C1 plus C3 and C1 equal to 1 and C2, then C2 equal to 2, then you see that this implies C3 equal to 0. Then you see that so this portion is a linear combination of the basis of this is the basis of S. So this portion is a linear combination of the basis of S. So this should be belonging to S. This portion belonging to S. So this vector belonging to S. So this vector gives you 1, 1, 2 plus, and this is a null vector. So you see that this is a projection of of 1, 2 because we get in things because this is belonging to S. So same vector is a projection of into S along T. Another example, if you consider another example, another vector, say, for example, if you take here it is 3, if you take 1 to 1, then you see that again you write this vector as linear combination of these three vectors. Then you see that C1, C3 equal to 1, C1 equal to 2, C3 equal to 1. So since C1 equal to 2, this means C3 equal to C1, C3, C2 equal to 1. Sorry, C2 equal to 1, because just see that C1, C3, C1, then C2. Now C1 plus C3 equal to 1, C1 equal to 2, C2 equal to 1. Then your C3 equal to minus 1. C3 equal to minus 1. So therefore, two into C2 equal to and C3. So you see that this portion or this vector, which is a linear combination of the basis of S, so this belonging to S, and if you simplify this thing, then you get 2, 2, 1, this belonging to S, and this vector belonging to T, then 2 to 1 is a projection of what? This vector 1 to 1 into S along T, and minus 1, 0, 0 is a projection of 1 to 1 into S along into T along S. So clear what is projection? Please tell me. Up to that, if have any problem, if you have any query, please tell me. Can I rub this portion? Yes. Shubhrojit, tell me, can I rub? Can I rub this portion? Okay, thank you. Anybody, please tell me if you have any doubt. Or or tell me, or no. Okay, thank you. So so homework. Take V equal to R4. S is equal to collection of X, Y, Z, collection of the vector x1, x2, x3, x4 such that x1 equal to 2x2, x3 equal to 2x4. Then construct all possible ortho, all possible complementary space actually I want to mean, if you consider our previous example, V equal to R cube, just explaining this part, what do you mean by this? Then your S is so the space generated by the basis okay. Now if you consider canonical basis of R cube, then you see that except this vector 0, 0, 1, you have two vectors, that is 1, 0, 0, 0, 1, 0. If you take any one of these, then you get T. Either you take this is a 1T, and if you take another, this one, then you get another T. So here it is, here you can construct two possible complementary subspaces T1, T2, where S is given. If your S is, if the structure of S is like that, in that situation you construct two complementary spaces T1 and T2. So in this homework, your problem is to construct all possible complementary spaces, that is Ti, where your S is like that. Okay. Then for next job, for given S, then you have, suppose you construct 5 TIs, 2 TIs for this example. When your V is RQ, then this S comma T1 and this S comma T2, these two possible ways, and each possibilities your problem is to represent the vector R4 or represent or write this vector as a sum of two vectors x car y car, where x car belonging to S and y car belonging to Ti. Okay, so first the problem is to find all possible complementary spaces of S, then decompose this vector as a sum of two vectors, where first vector belonging to S and second vector belonging to Ti. So here, please tell me if you have any doubt. Please tell me. First, this is the S is given. Next, you construct all possible complementary spaces of S. Video. Uncle, tell me now, it is okay or not? Now, now, Uncle, is there any problem? Okay, thank you. So, your S is this. Okay. First, your job is to construct all possible complementary spaces. Then for each pair, S and Ti, you write this vector as a sum of two vectors, where first vector belonging to S and another vector belonging to T. So this is your homework. If you have any doubt regarding this homework, please tell me. Okay. See that if you consider RQ, okay? Your S is can you see this thing? Subhajit, wait, I am answering your question, okay? X, y belonging to R. Another way you can write this as now if you take t equal to, so this is the one possibility where RQ equal to S plus T. I denote this T1. If you take another T2, T, that is, I denote this T2. So this is your, again you write this as the sum of these two subspaces. Now suppose you take a vector 1 1 1, then you write 1 1 1 as a linear combination of the vector x card plus y card, where x card belonging to S, y card belonging to P1. So problem is find x card, y card. Here also you write x1 card, y1 card, x1 card belonging to S, y1 card belonging to T2. Problem is to find x1 card, y1 card. So first you solve this problem, this homework, then do same thing for this. When your v equal to R4, your S is given, then you find all possible complementary spaces. In RQ cases, this is T1 and T2. So in R4, you find first you find T1, T2, T3, the all possible complementary spaces of S. Then represent it. Then represent this vector as the sum of two vectors x card plus y card, where x card belonging to S, y card belonging to Ti, and find x card, y card. So this is the problem. Okay, Ankon, Shubhrojit, please tell me. No, complementaries should not be same. If you divide Shubhrojit, you say, sir, if we divide the basis in two parts, then complementary should be same. No. You see that in the case of RQ, your complementary this or this. These are not same things. Okay. You can check. T1 and T2 are not same things. Subhajit, are you there? Please tell me, are you agree with me or not? See that T1, T2 are not same. Okay. So homework clear? If you have any doubt about this homework assignment, tell me. Or continue. Can I continue? Ankon, if you have you any doubt? Okay, thank you. Now, this is a detailed sum. This is the collection of vector. Now, we write this x curve, which is a projection of u curve on into S along T. I denote this projection by PU curve. I already observed that if this U curve belonging to S, then this U curve is nothing but a PU curve, which I already observed in the example R cube. So why this thing happened? See that x curve, if you take x curve equal to PU curve, then U curve equal to PU curve, and Y curve should be U curve minus PU curve. This is your Y curve. This is your X curve. Clear? Okay. So since U curve belonging to S, this implies, and this belonging to T, this is only possible when U curve minus PU curve equal to 0 curve. This implies U curve equal to PU curve. Therefore, PU curve equal to PU curve. Now, P U1 curve plus U2 curve equal to P U1 curve P U2 curve. Another case, U1 curve for all U1 curve U2 curve belonging to S plus T. Now U1 curve belonging to S plus T, this means U1 curve uniquely decomposed by two vectors, x1 curve plus y1 curve, while x1 belonging to S, y1 belonging to T. So x1 should be E1 curve. Similarly, U2 curve belonging to S plus T, this U2 curve written as a uniquely by two vectors x2 curve plus y2 curve, where x2 curve belonging to S, y2 curve belonging to T, then this x2 curve is nothing but a P u2 curve. Therefore, u1 plus u2, this is x1 plus x2 plus y1 plus y2. Therefore, x1 curve plus x2 curve, this is nothing but a P u1 curve plus u2. Hence, P u1 curve plus u2 curve, x1 curve plus x2 curve, where x1 curve equal to P u1 curve, x2 curve equal to P u2 curve. Hence, next claim, P lambda u curve equal to lambda u curve. So lambda u curve equal to lambda x plus y curve equal to lambda x curve plus lambda y curve. So P lambda u curve is nothing but a lambda x curve. Again, x curve is P u curve. F2. Now, orthocomplementary space. Suppose V is your inner product space. V is your inner product space. S is a subspace of V and is given. Then orthocomplementary space denoted by this way, which is a collection of vectors V curve, where V curve belonging to capital V, such that scalar product of V curve with any vector in S is 0 for all x belonging to S. This is a orthocomplementary space of S. Let x1 curve, x2 curve, xn curve be a basis of S. So using using Baum's optimization technique, you also get a complementary or orthogonal basis of S. So instead of any basis, I take orthogonal basis of S. Orthogonal basis of S. That is, scalar product of xi xj should be 0 for all I multiple. Take any vector beta curve which belonging to V, but beta curve does not belong into S. This is possible because S is a subset or subspace of V, so this is possible. This implies beta curve this is a set of independent vectors. The set of independent vectors. Now, using Gram-Smith optimization technique, beta curve to get a vector V curve, which is orthogonal to any vector which is orthogonal to any vector in S. So this V curve using Gram-Smith optimization technique, this V curve should be written as a beta curve plus sum over Ci xi curve I from 1 to n. Clear? Tell me. Please tell me. Instead of basis, I take a orthogonal basis of S. Since S is a subspace of V, we always get a vector beta which does not belonging to S, but beta belonging to V. So beta and together with beta and this vector x1 to xn, this collection should be a set of independent vectors because beta does not belong to S. This implies this collection should be a set of independent vector. Now our aim is to find V curve which is orthogonal to S, which is orthogonal to S. Then this V curve should be written as a linear combination, or this vehicle can be represented as this linear combination using Gram-Smith optimization technique. Okay. Second last line. Ankun. So Ankun, beta does not belong beta belonging to V, but beta does not belonging to S. Is it possible or not? Tell me. If it is possible, then tell me why it is possible. Ankun. See, Ankun, since V S is a subspace of V, so is it always possible? You get a vector beta which does not belong to S but belonging to V. Together with yes, Shubhajit, you are right. Together with this beta, this is a set of independent vector. Okay, Ankon. This is a set of independent vector. Now, if you want to find, see, what is the Gram-Smith optimization technique? Suppose you have a set of independent vector extend beta curve, then Gram-Smith optimization technique gives you a set of orthogonal vector. Because these vectors are already orthogonal, then you get this along with another vector v curve. This set should be an orthogonal vector, set of orthogonal vector, and the properties beta is orthogonal to any one of this xi curve. Since this is the basis of S, so this means V curl is also orthogonal of any vector which can be written as a linear combination of this vector. Hence, V curl is orthogonal to the vector space of S. So, for constructing V curl, we use Gram-Smith optimization technique. According to Gram-Smith optimization technique, you write V curl as where Ci is such that for all I, and your V curl is this implies Ci equal to for all I. Hence, V curl equal to beta curl minus sum over j from 1 to n I from 1 to n beta curl xi curl Therefore, therefore, beta curve, which is any vector, beta curve is any vector in V, but beta curve does not belong in S. Is written as a sum of two vectors. I write this vector as a x curve. So this decomposition gives you V beta curve which belonging to V, but beta curve does not belong to S, and x curve which is a sum of, which is a linear combination of the vectors of a basis of S, hence x curve belonging to S, and V curve which is orthogonal to any vectors in S, so V curve orthogonal to S. That means V curve belonging to orthocomplement space of S. Therefore, X curve is a projection, not only projection, this is an orthogonal projection this is an orthogonal projection of beta curve where on S. So X curve is an orthogonal projection of beta curve on S. So please tell me if you have any problem. So please tell me if you have any problem. So check that. This is your homework. Scalar product of x curve v minus x curve equal to 0. Homework. Now, we already see that for given S, you get a complementary space of S, and for each complementary space, you can decompose V curve by two vectors, one belonging to S, another belonging to, say, I think it is better to write Y curve. One belonging to S and another belonging to Y curve. Another belonging to T, which is a orthocomplementary, which is a complementary space. Orthocomplementary space is itself a complementary space. So now, if you take the norm of actually this V curve, you realize your V curve by this projection of Y curve. Because in estimation technique or estimations, linear model, if you consider linear model estimation, mainly in estimation problem, your parameter is unknown. You realize your parameter through statistics, which is nothing but a projection on estimation space. So your vehicle is unknown. Suppose your vehicle is unknown, or you want to realize vehicle or your space S, and the realization of vehicle is vehicle on your space is S. Now you want to check your realizations, how close your realization to vehicle. For this you need to take norm of vehicle minus y curve. Here I take square of this norm functions. You know the norm functions, that is norm defined as a scalar product of vehicle vi square. Anushka Roy, no sir means what? Sohini, you also say no sir. Suraj Kumar, you also say no sir. Please tell me what is your problem? Can I continue, or if you have a doubt, tell me. Anushka, Sohini, Suraj, please tell me. Have you any doubt? Oh, sorry. Thank you. Actually, I forgot what I am asking. So the norm is defined as root over what is. Suppose if you have a we have a n component, then the norm defined as this. So my question is, this is your realizations of vehicle on S. Now this realization, how your who's your realizations, or suppose and for this you should take a norm of vehicle minus y curve, and I squaring this two part, this part. So x curve is your orthogonal projections. Instead of projection, if you take a orthogonal projection, then you write this as now. This is simply as since check, use this result here. See, v curve minus x curve is this, and x curve minus y curve, x curve minus y curve belonging to S. This is nothing but x curve. You can keep this as x curve, or you break this part into two parts. V curve x curve minus curve, x curve, y curve. Since y curve belonging to S and V minus x curve belonging to orthocomplement space of S, then this should be 0. So this is equal to, so norm always greater than equal to 0. This means this implies so interpretation of this result, instead of any projection, if you take a orthogonal projection, then the distance from the curve is minimum. So this is the principle of least square technique. Actually, in least square technique, we use orthogonal projection instead of any projection. If you look at this diagram, you see that. So this is your orthogonal projections. If you take any of this, you see that the perpendicular distance is the minimum distance. So this is the philosophy of least square technique. Actually, in least square technique, we use orthogonal projection instead of projection. That means you divide two vector spaces. That is your S. S is your estimation space and S complement, ortho complement. This is your error space. And this gives you a parametric space V. So any vector in V which is unknown, and you can realize this vector through the projection of any vector in S, through the projection of a vector in S. So this is the principle of least square technique. Clear? So you can check this via an example. Suppose your V is RQ. You take S is a collection of this, and the basis of S is okay. In this square principle technique, instead of any projection, we take a orthogonal projection. We already see that instead of any projection, if you take a orthogonal projection, the distance is minimum. Okay, uncle. So this is the principle of a least square technique. Actually, in linear model, you divide your parametric space into two parts. That is the estimation. Okay. Wait. Tell me, Dishari, now is it visible? Now, Dishari? Network problem. Okay. So please tell me, if the thing is clear, tell me, then I will start. Okay, Deshrik, I continue. If you have any doubt, please tell me later. Wait. Okay. So, Ankul, you have a still doubt or tell me? Ankul, you have a still doubt or tell me? Can I explain more or continue with this example? Ankul, clear what is the idea or philosophy of a list square technique? Actually, in list square technique, we use orthogonal projections instead of two spaces. Sir, please explain the two spaces of V. Two spaces of V means? Oh, actually, in list square principle, we already see that in this calculation, if you take instead of any projection, if you take orthogonal projection, then the distance from V is minimum. Okay, so if the distance is minimum, this means if your realization is better than any projections because it is close to V. than any other projections. So this is the principle. This is the principle of the least square technique, and in our linear model, we define two spaces of V. That one is estimation space, another is error space. Error space is a orthocomplementary space of estimation space, and and your unknown parameters which lies in your V, this can realize through a vector in estimation space, and this this is a this is obtained by using least square technique. This least square technique is nothing but a orthogonal projections or constructing the orthogonal projections in estimation space. Okay, clear, Ankul? So if you have a more doubt, so please tell me after the class. Now, in our example, if you take V equal to RQ and S is equal to this, the basis of S is now, instead of using, so you check that this is a orthogonal basis, because the scalar product of these two vectors is 0. Now, if you take any vector, now your any vector which does not belong into, so if you consider the vector along with this vector, if you consider this vector along with this vector, then you see that this is a set of independent vectors. We have already seen this thing. Set of linearly independent vectors. Now, using Gram-Schmidt orthogonalization technique, so or another way, so this is a okay, this is a orthogonal basis. Now I want to find X card which is a orthogonal projection with a vector y card which belonging to, say, y, if you take your y card is 1 1 1. Okay. See that this 1 1 1 does not belong into S. So along with this is a set of linearly independent vectors. This is a set of linearly independent vectors. Degrees of freedom is nothing but a dimension of the vector space. Okay. Degrees of freedom is nothing but a dimension of your estimation space. Clear, Ankon? Error space is nothing but a orthocomplementary space of estimation space. So now one your y curve, your x curve, because I want to find x curve written as a linear combination of using Brown-Smith orthogonalization technique, linear combination of these two vectors, these three vectors, using Brown-Smith orthogonalization technique. Now, see that this x curve is orthogonal with these two vectors. If the scalar product imply this is 0 equal to 2 plus 2c1, c1 equal to minus 1. Again, is equal to c2, c2 equal to minus 1. So x curve is nothing but a 1, 1, 1 plus, sorry, minus the null vector. So your orthogonal projection is the origin of this vector, because if you look at this vector, you see that this vector is belonging to S. For that reason, your projection is nothing but a null vector. So if you take another vector for getting non-trivial result, 1, 1, 2, this does not belonging to S. So this is written as a sorry. This is again belonging to 2. I just need that little adjust. If you take y curve 1, 2, 1, this does not belong to S. Then 1 to 1. So it's same way 1 to 1. Uh, This is 3. So C1 equal to minus 3 by 2 minus 1. So x squared three by 2 1 1 0 so 1 minus 3 by 2 2 minus 3 by 2 1 minus 1. This is minus half half 0. So this is a orthogonal projection of the vector in on S. Clear? So or you can use the direct formula which we gave, that is sum over I from 1 to n exciter v exciter exciter. So you can also use this direct formula or can get in that way also. So this is the orthogonal projection of x squared. And if you take S is equal to, if you take your t equal to then you see that the vector 1 1 to 1 is written as a linear combination of one 1 0 2 into 1 0 0. So this gives you 1 2 plus 0 0 1. So this portion is a projection of, we simplify it as 1 2 0. This is nothing but a projection of projection of 1 to 1 into S. So this is the any projection and this is the orthogonal projection. And if you look at this, you take norm of this, so it is x curve. Sorry, this is your v curve. Sorry, this is your v curve, and I denote this by y curve, and it is your x curve. Now look at this v curve minus y curve. That is norm of simply 1, and v curve minus x curve one to one minus half 0. This is half 3/2 . So you can check this thing in your okay, so now I think there is a problem. So can you hear me? Then I tell something. Can you hear me or not? Okay. See that you can. I almost finished my class. So your homework is you just check this thing. If you take this, okay, you take another projections, that is 1 to 0. You see that this is another projections, and look at that. The distance from this v curve minus x curve, this norm function, should be less than v curve minus y curve. You check this thing. Check. Subhrojit, can I say? Now, which portion you cannot? Is it a network problem or? Can you see the board or not? Tell me. Okay. So the job is, your homework is, you take, I already in my previous example I already take some PIs in RQ cases. So in every cases you find the projections of 1 to 1. Okay, you find the projections of 1 to 1, then take the norm of v curve minus y curve. Y curve is your projections of v curve into Ti, and then you find the norm of v curve minus x curve, where x curve is a projections of x curve is a projections of orthogonal projections of one-to-one or V curve, and you see that this norm is greater than this norm. Okay, so this is the third homework, and fourth and fifth. So considering V equal to R4 and find S is your, I forgot, I think I give this S now. Please tell me if I am wrong. Where x1 equal to x2, I think x3 equal to x2. So take V equal to this. Okay. Take V equal to this. Then find orthogonal projection of V curve, and it should be unique. Orthogonal projection should be unique. I will put this later. So find orthogonal projection of V curve, then denote this by x curve. Denote this by x curve. Then check that x curve minus V curve minus x curve is less than V curve minus y curve, where y curve is any projection of V curve on S into S. Similarly, you consider another homework. V equal to R5, V curve equal to 1, 1, 1, 1, 1. S is equal to x1, x2, x3, x4, x5, where x1 plus x4 equal to 0, 2x1, x3 plus x4 equal to 0. Find all possible complementary space find complementary space, no, then find norm of V curve minus y curve for all complementary spaces also check that the distance is minimum when the corresponding complementary space is orthocomplementary space. Corresponding T is orthocomplementary space. And last, the representation of vector, since the representation of this vector v car x car plus y car, where x car belonging to S, y car belonging to orthocomplementary space, this representation is, this decomposition is unique. It is obvious because if it is because it is a direct sum, it should be unique. So orthocomplementary space should be unique. So I think Shubhajit asked me a question. Shubhajit, probably you asked me a question that, or you said this thing, complement should be unique. It should be unique when it is an orthocomplement. Otherwise, it is not unique. Clear? Shubhajit, I think you stated this thing. Complement should be unique. It is not true. If it is orthocomplement, then only then this is unique. Otherwise not. So if you have any doubt, please tell me. I give you 5 minutes, and after that I end the stream. Please tell me, anybody, if you have any doubt, please tell me. I will explain. If not, then I will end the stream. So please submit the all assignment before next class. So in my next class, I will discuss linear transformation. So thank you. So, or if you have a doubt, you can call me or mail me. I will definitely answer your questions. Thank you.